We are graphing a rational function, and we're asked to first find all the asymptotes, intercepts, and our holes, and then we'll use that information to plot it on the Cartesian plane and then graph the function. So the first thing that we want to do is start off by simplifying this rational function as much as possible, and we do that by factoring the top and the bottom. Well, the bottom's pretty easy to factor. We can just call this x plus 4 times x minus 3. In order to factor the top, let's take a look at that a little bit more closely. Let's use the AC method followed by the grouping method to factor this trinomial. We'll take A and C, multiply those together to get 6, and we're looking for two factors of 6 that are going to add to the center term. Well, that would be 6 and 1, and in order to get a negative 7 out of that combination, I'm going to need both of those to be negative. So we have negative 6x minus x. That's going to be how we rewrite negative 7x. So we end up with 2x squared minus 6x minus x plus 3, and then now we use our grouping technique. So we're going to group the first two terms together and then factor out the common 2x, which would leave us with x minus 3, and we need to get an x minus 3 from the second group as well, which means that we'll need to factor out a negative 1 in order to get x minus 3 remaining. Now we factor the common x minus 3 out of both of these terms, so we're going to have x minus 3 times 2x minus 1, and this is how the numerator factors. So back over here, let's pop in that factorization, and then now we see that the x minus 3 terms are going to cancel, so let's simplify this. We'll have 2x minus 1 remaining in the top, x plus 4 remaining in the bottom, but we do need to impose the restriction that x could not be equal to positive 3. We lost that in the cancel step, but we still have it as a domain restriction, so it needs to be imposed at the end here. Now let's talk about what is the domain. We can see the domain restriction that x cannot be negative 4, and we impose the domain restriction that x could not be equal to 3. So let's just state the restrictions that x cannot be equal to negative 4 and x cannot be equal to 3, and then we'll take that together to get the domain in interval notation. So we'll say negative infinity to negative 4, union negative 4 to positive 3, union positive 3 to positive infinity. Again, both of these are domain restrictions. This one you can still see through the simplify step, and that one had to be brought back since we lost it in the cancel step. The vertical asymptotes occur at the zeros of the factors that remain in the denominator, right? And so the factor that remains in the denominator through the simplify step is the x plus 4. So the vertical asymptote is going to be the vertical line that is negative 4, which is the zero of that factor that remains in the denominator, right? Basically, we cannot cross that vertical line because it's a domain restriction. In order to get the horizontal asymptotes, we're going to consider the degree of the top and the bottom. Let's look at it from the simplified version. We see that the degree of the top is 1, the degree of the bottom is 1, and so in this case we're going to get the horizontal asymptote that y is equal to the ratio of the leading coefficient. So we're going to do leading coefficient of the top over the leading coefficient of the bottom. Basically, that's going to be y is equal to the leading coefficient of the top is 2, and the leading coefficient of the bottom is 1, so y is equal to 2 over 1 can be simplified down to just being y is equal to 2. Now, because we have a horizontal asymptote, we are not going to have an oblique asymptote. You can't have both horizontals and obliques. We also have a vertical asymptote, and we're going to put that on our Cartesian plane here in just a minute. But before we do that, let's find our x and y intercepts. Remember, in order to find the x-intercept on any function, we're going to plug in y is equal to 0 and solve for x. In order to find the y-intercept on any function, we're going to plug in x is equal to 0 and solve for y. So here's the simplified version. Now let's plug in y is equal to 0 and solve for x. And in doing that, we are able to really just consider the equation portion and not this additional domain restriction. Let's just make a mental note that x cannot be 3. That's actually going to end up being a hole in the graph. So as long as it doesn't turn out that x is equal to 3, we should be fine. So now that we've plugged in y is equal to 0, we're going to solve for x. But remember, this is now a rational equation in one variable, and we solve that by multiplying both sides by the LCD. So we're going to multiply both sides by x plus 4. On the left-hand side, we still have 0, and on the right-hand side, we're going to get the denominator to cancel, so that's going to be 2x minus 1. Now, we'll add 1 to both sides, and then divide both sides by 2 to get that x is equal to 1/2. That is our x-intercept. We'll clarify that by writing it as an ordered pair, that the x-intercept is going to be at 1/2, 0. In order to determine the y-intercept, we're going to plug in x is equal to 0. Basically, that's the same thing as evaluating the function at 0, and that's going to look like 2 times 0 minus 1 over 0 plus 4, which is negative 1/4. So let's finalize our y-intercept by saying that it is the point, the ordered pair, 0, negative 1/4. Let's make one more mention of that hole. Remember, at the beginning, we saw that we had this domain restriction that was the thing that canceled out. The holes are going to occur at the domain restrictions that canceled out. So this is going to be a hole in the graph. We'll see what that looks like here in just a second. But for right now, let's just state that we're going to have a hole at x is equal to 3. So now we're going to take all this information and put it onto our Cartesian plane. So starting with the asymptotes, let's look at the vertical asymptote, x is equal to negative 4. Let's also label all of our asymptotes and intercepts. Then we have y is equal to 2. That's going to be a horizontal line. We have an x-intercept here at the ordered pair, 1/2 and 0, and then a y-intercept, 0, negative 1/4. In order to draw the graph, we see that we're going to need to pass through these two intercepts, but also approach the asymptotes. And in order to approach the two asymptotes that I have here, I'm going to need to draw in my graph like this. And I do want to come down here and approach this vertical asymptote, but we are not going to cross it, right? Because vertical asymptotes happen at domain restrictions, you cannot cross them. In order to see what's going on with the graph over here, let's first of all make note of the fact that we must have graph in that region because the domain of this function was from negative infinity to negative 4, and then union negative 4 to 3, and then union from 3 to positive infinity, which means we have graph in all those regions. So this region here is included in the domain. I must have graph there, right? And I also know that there are no more x-intercepts over here. We calculated the x-intercepts and we only found 1. So I cannot possibly do this because that would have me crossing the x-axis again, and I know that I don't cross the x-axis. So it must be that we approach the asymptotes up here in this region. We're going to approach it on the top side. Now, the other bit that we see is that we have this portion here from negative 4 to positive 3. We do know that there's going to be a hole at 3, so it's time to figure out where that hole has to be. So we see that x is equal to positive 3 right here. So we're going to look at where the graph is occurring at x is equal to 3. It looks like it's happening right about here-ish. So let's come in there and basically just erase a section of the graph and replace it with a hole, right? This is where x is equal to 3, and that's where our hole is going to be located. Now, we can just kind of eyeball it a little bit like this, but in order to get a more accurate elevation, like how high is that hole? What would be the y value where that hole is existing? I know the x value would be 3, but what would the y value of that hole be? In order to determine that, let's look again at the equation. This is the equation, and we had to manually impose this domain restriction. In order to see what the graph would be, or what that elevation would be without the hole, we simply say, well, let's just take out that domain restriction and plug in the x value to the function that wouldn't have a hole unless I manually imposed it. So basically we just plug the domain restriction into that simplified version to see what the elevation of the hole should be. So that would be 2 times 3 minus 1, and then 3 plus 4 in the top. So this would be 5 over 7, which is actually a little bit less than 1. So at 3, we would have a hole that's a little bit less than 1, and the approach to the asymptote is a little bit more gradual. We would then label this hole with the ordered pair. 3 and 5/7 is the elevation, or the final position of where that hole is existing. So now let's come over to the calculator and input our function. I've already done that here, and then go over to the graph, and we can see that our graph is pretty similar to what the calculator is giving us. Let's verify a couple of our ordered pairs by going second, calculate, and then the value function, so hitting number 1 here. We'll calculate our y-intercept to make sure we got that in the right spot. Yep, y is equal to -1/4, looks good. Let's also calculate our x-intercept, so we'll do x is equal to +1/2 just to make sure that we do get a y-coordinate of 0, and we do. And let's see what would happen if we calculate x is equal to the domain restriction 3. This is the one that's supposed to have the domain restriction, right? So we calculate that, and look, we see that there is no corresponding y value. That's because there's a hole at x is equal to 3. So there's no output when x is equal to 3, and that's how we can verify that we actually do have a hole.